Hey kiddos, and welcome to Hess's Law 11.4. So this is actually so much fun. You're gonna just love it. It's so much fun. You're basically solving problems with kind of like puzzles. Yeah, so let's do this. Not all chemical energy changes can be studied conveniently using simple calorimetry, so we have to find different ways, and this is one of those ways. Methods used to study these reactions are based on the principle that net changes in all properties of a system are independent of the way the system changes from the initial state to the final state. Okay, good times. A lot of times when I read something, I'm like, I think about you guys going, do you even understand? This will all make sense in a bit. So, ready? Hess's law states that the addition of chemical equation yields a net chemical equation whose enthalpy change is the sum of the individual enthalpy changes. That is what Hess's law is. Oh my goodness, do you even know what that means? Because when I first read it, I'm like, I don't even understand what you're saying. Like, what are you saying? And even better is this. Here's the formula that you use. And all of a sudden you look at this and you're like, okay, what? What am I going to learn? I'm going to lose my mind. But you're going to see that it's actually quite simple. And then when you go back and you read this law, it'll all make sense. So here's a note. Hess's law enables us to determine the enthalpy change for a chemical reaction, which is either too small to be or impossible to be measured by a conventional calorimeter. Cool. So basically they're saying if you don't have a calorimeter, there's different ways of finding the change in enthalpy of a reaction. Hess's law allows us to calculate mathematically the enthalpy change for a reaction without actually doing the calorimetry. Cool. So here's our mathematical formula, which seems really long. Like, why am I taking the whole screen to write this down? Don't even worry about it, because it's all going to make sense. So 2 things to remember, kiddos. Very important things, super easy. If a chemical equation is reversed, then the sign of the change in enthalpy of reaction changes. So what does that mean? So if I have A plus B yields C, and my delta H, let's say, is 1 kilojoule, okay? And it's positive 1 kilojoule. Let's say that for my A plus B, these are, in this example, they're the reactants. Let's say I want to make them products. Then I'm flipping. Do you see what I'm doing? I'm allowed to flip this reaction. Because I flipped this reaction, I went from reactants to products. I have to flip the sign. So now my delta H is negative 1 kilojoule. All right, kiddos? The next point that's really important says here, if the coefficients of a chemical equation are altered by multiplying or dividing by a constant factor, then the change in enthalpy of reaction is altered the same way. Okay, let's say again I have A plus B yields C, and let's say my delta H is positive 1 kilojoule. And let's say I need 2 C's. I need 2 of these. I need 2. Let's just say, for example, in order for me to get a coefficient of 2 here, I have to multiply everything by 2. So this becomes 2A plus 2B yields 2C. Now notice I multiplied everything by 2. I can't just multiply one thing by 2. I have to multiply everything by 2, including my change in enthalpy for the reaction. So my delta H then becomes 2 kilojoules. So if I flip the reaction, I have to flip the sign. If I multiply the reaction by a certain factor in order to change the coefficients, I have to do the same thing to the delta H. Okay, kiddos? So those are the 2 important things. Very important. So here's a good example of something that you might come across. Use the following formation reaction evidence to calculate the standard enthalpy change for the complete combustion of cycloheptane. Okay, cycloheptane is C7H14. You don't know that yet, but you will soon. And I have 3 pieces of data or evidence. Here's my data or evidence, right? If this is my evidence, I need to use these 3, up to 3. You can use all of them, some of them, but typically it's all of them, but not always, in order to get a balanced equation. So my step number 1 is I need to obtain a net reaction or a balanced equation. Sometimes you're given the balanced equation, sometimes you're not. Sometimes you actually have to complete the balanced equation. Now let's just take a quick look and remember those 2 steps. I'm going to talk about them a little bit. Notice that here's my cycloheptane. Notice that it's a reactant here. And notice in my evidence pieces, let's see where it is. Where is it? It's right here. But here it's a product. No good. No bueno. I have to change this to a reactant, so I have to flip. If I flip the equation, what happens to the sign? Just saying. You're going to see the answer, but I'm just saying. Another thing that I need to look at is I have 14 carbon dioxides, right? Because these three have to be added together to get me this. So notice here I have 14 carbon dioxides. And so back to my evidence, where do I see carbon dioxide? I see carbon dioxide right here. But there's only one of them. So if there's one of them, that's not going to help me. I need 14 of them. So in order to get 14 of them, I have to multiply everything by 14. Does that make sense? 14 carbon, 14 oxygen, 14 carbon dioxide, 14 of these. Okay, so that's just a quick glance. Already you can see what you can do. So step number 2, manipulate the given equations so that they will add up or yield the net equation you made, or the balanced equation. Be sure that all of the compounds or elements of the given equations are on the appropriate product or reactant side so as to match the net equation, and also make sure that the coefficients are the same. So reverse or flip the equation if required. Also by manipulating the coefficients by multiplying or dividing. So those are my 3 pieces of evidence, and what I've done here is I made sure there's 14 carbon dioxides, and I also flipped and multiplied by 2 because I need to have a coefficient of 2 for the cycloheptane. Okay, kiddos? So now that you figure all this out, and sometimes what you have to do too is you have to multiply things as well just to get rid of things, and this will all make sense in a bit. And also here, notice how these 2 oxygens are both in the reactant side. If they're both in the reactant side, these are added. You add the coefficients. Now notice how I have 14 hydrogens on the reactant side, and then I have 14 hydrogens on the product side. Because they're the same, but one's on the reactant, one's on the product side, they actually cancel out. All right, kiddos? Notice that there's 14 carbons here, reactant, 14 carbons here, product. They cancel out too. They have to cancel out. They have to. Because if I have a reactant and the product and they're exactly the same, they're going to cancel out. So I'm just showing you in a neater way. Step 3, cancel all the reactant and product pairs that are possible, then add the rest together and you should get your net equation. So remember what I told you? So I have oxygens, both on the reactant side, those have to add up. And then everything else, you just kind of go down and create this new balanced equation, okay? So see, I have, this is reactant number 1, which is right here. And then I add these 2, and this becomes reactant number 2. And then the rest are products, and the only products I have, 14 carbon dioxide and 14 water. Then if I flip or whatever, if I flip the equation or I multiply by a coefficient, I have to make sure this is all treated equally and the same. Like if I flip something, I have to flip the sign. If I multiply everything by 14, for example, I have to, this would be delta here. I have to flip the delta H sign. Then I'm going to add these all up to get me the total change in enthalpy of reaction. Okay, and that's what you do. So that's not too bad. Here's a second sample problem. Use Hess's law to determine the standard enthalpy change for the formation of carbon monoxide. So I have to figure this out. The change in enthalpy of formation of this guy using these 2 pieces of evidence. Okay, so really quickly, I have carbon on reactant side, carbon on reactant side, cool. Carbon monoxide has to be on the product side. It's on the reactant side, I have to flip it. And also, there's a 1 here, and there's 2 here. So I have to probably divide all of this by 2, including this guy. And what else do I have to do? Oh, look, see, notice that there's a carbon dioxide here? I have to make that go away because there's no carbon dioxide here. There's nothing. So I have to make that go away. So you play around with it until you get your answer. So rearrange the equations so that you obtain the chemical equation for the formation of carbon monoxide. Okay, and remember I changed, here, something happened here, right? I had to divide by 2. And then Add the reactants products as standard enthalpy changes to get a net reaction. Notice how there's carbon dioxide in the product side, carbon dioxide in the reactant side, the same amount. These go away. And notice how there's one oxygen here, but only half here. So you're actually subtracting them because I have one on the reactant side, only half on the product side. So this goes away and this becomes half. Does that make sense, kiddos? And that's where this came from. All right, so here's another example. Oh, actually, this is the answer. This is just your formation of carbon monoxide, the reaction. This is the potential energy diagram. All right, so that's just a little something from the previous unit. Here's another example. In an experiment to find the standard molar enthalpy of formation, okay, so now it's molar enthalpy. Now we have to make sure we know it's kilojoules per mole, okay? Of formation of butane from its elements, the following values were determined by calorimetry. So we use a calorimeter to get this data. So there are 3 pieces of evidence, and I have to use these 3 pieces of evidence and play around with them, flip them, multiply them, whatever, in order to get a balanced equation where it's the formation of a butane. Okay, so here's the balanced equation. I have 4 carbons plus 5 hydrogen yields 1 butane. You need to make sure the coefficients of the balanced equation match. Keep in mind that butane is a product, not a reactant. Fix that. Okay, so there's the information that we have. Here's my butane. It's a product. Here it's a reactant. That has to be fixed. And there needs to be 4 carbons. Notice that there's 4 carbons here. And notice here there's only 1 carbon, so I have to fix that. I have to multiply everything by quattro, right, including this guy. And this is flipped. We're going to flip the first one. So make sure the sign gets flipped because this is a reactant, needs to be a product. Okay. There needs to be 4 carbons, 5 waters, and 1 butane. Here's my, or 5 hydrogens. Oops, 5 hydrogens. So where's my hydrogen? Oh, there needs to be 5 here. So what are you going to do? What are you going to do to get 5? Good times, right? Multiply by 5 over 2. Yes. So that, yeah. Anyhow, go ahead and do your magic in order. You're looking for standard molar enthalpy formation of butane. Lucky there's only 1 butane. Notice here how there's 1 butane. So it's going to be already over 1 mole. All right, so these are the things that you have to do, and you have to cross out. Remember, there's 4 carbon dioxides here, 4 carbon dioxides here, they cross out. 5 waters, 5 waters, they cross out. Okay, so basically we get a total molar enthalpy, change in enthalpy of formation of negative 125.6 kilojoules. There happens to be 1 mole, so it's just over 1 mole, which is the same. If this had a coefficient of 2, obviously you divide it by 2 moles, and then you get a different answer per mole, but it's not, it's 1, so we're good. Okay, that's it, that's all. So it's just basically either flipping a reaction or equation, I should say, or multiplying an equation by a certain coefficient in order to make your data match the balanced equation or the net ionic equation. All right, have fun.